Hi, I'm Chi. We present our novel work on communicative learning with natural gestures for embodied navigation agents with human in the scene in a VR environment. This is the overview of our presentation. Let's start from the background and the motivation of this work. Gesture is a form of nonverbal communication with visible bodily actions. It could be your hand motions, body languages, or facial expressions. It plays a significant role not only in human-human communication, but also in human-robot communication. Let's take the following case as an example. Here, our task is to instruct the robot to clean the circled area. To complete this task, the human player and the robot must have the joint attention on the target. And here the question is, how could we convey such message to the robot? In a language-only scenario, in order to refer to the exact location, we require a lengthy text to express our intent. We may say, clean the area on the table close to the second chair in front of you. In contrast, gestures allow to express the same message in a much simpler and more natural way. For example, we can say, clean here while pointing to the target location. In this way, the human message could be correctly interpreted with a joint understanding of the scene and the semantics of gestures. Such multimodal messages are more succinct, immediate, and intuitive. Inspired by the significance of gestures in human-robot communication, we intend to bring nonverbal communication cues into the embodied agent navigation task, the most straightforward task of an embodied AI that interacts with the environment and other agents. We contemplate on a few questions and ultimately want the agent to solve two problems in our framework: multimodal target inference and navigation. We think they should be mutually beneficial, that is, learn to communicate and communicate to learn. Before we talk about our work, let's take a look at some previous works. Visual navigation has made significant progress in the last few years for the embodied agent with the advances of deep learning models and the development of simulated environments. Advances in vision and language understanding have enabled a visually grounded language navigation agent to be trained. Those works are referred to as vision language navigation. There are many different tasks completed under this framework, including instruction following, embodied question answering, interactive question answering, and so on. Despite using verbal cues for the visual navigation, there are also existing works incorporating other modalities, such as target images, semantic priors, acoustics. However, they are not concerned with speech. Our work is built on the existing VLN framework, but extended by incorporating gestures as a new modality for communications. Gestures have been used as a communicative interface between human and robots in robotics. Prior literature typically predefines gestures with their meanings. For example, OK sign means approval. In our work, we want to develop a flexible system that could uncover the semantics of natural gestures without predefining their meanings. Our contributions could be summarized as the following. In short, we developed a simulation framework that supports multimodal interactions with human users and demonstrate that the embodied agent could improve its navigation performance with gestures and understand the underlying semantics. In this section, we'll talk about more details of our simulation framework. Our simulation framework is named Ges-THOR, which is the shorthand for gesture-based THOR. In this framework, the human players could interact with the simulation environment, whereas the AI2 THOR environment and multiple sensory devices reside. This environment could generate observations from different modalities: RGB and depth images, object category, and gestures. Those observations are sent to an RL planner where sampled actions are taken by the embodied agent in the environment. Let's break down this framework and see how each component works. As the name of our framework indicates, we build our simulation framework based on the ISOR environment from AI to THOR in Unity. The reason we choose this environment is because it has diverse layouts from different room types and has thousands of unique objects with physical simulation. Aside from that, Unity has good compatibility with different sensory devices. We integrate Oculus Rift, Connect V2, and Leap Motion Controller with our environment to enable human-robot interaction. This example shows how those devices work simultaneously in the VR environment. Oculus Rift immerses human players in the virtual environment, while Connect V2 and Leap Motion tracks the body and hand motions. In the following slides, we'll show you how we record gestures for the embodied task. In our dataset, each task is defined with environmental information and gesture information. In this example, the task for the robot is navigating to the chair from its initial position. We have two types of gestures to instruct the agent. One is referencing gesture. The human player communicates with the agent to guide the direction, for example, pointing with a finger. The other one is the intervention gesture. The player shows gestures in a rejective manner used to warn the agent if it is moving away from the target. The motions of the human players are saved as a sequence of features. Each frame contains the positions and the rotations from different track joints, and they are encoded as a feature vector. Here are some examples of our recorded gestures in different scenes. Our dataset contains a diverse collection of referencing and intervention gestures covering different room types and object types. They'll be used for our navigation tasks. In the next chapter, we'll go over our navigation task and the learning network. In this work, our agent is required to reach the target object in a simulated environment with different observations. It could turn left, turn right, move forward, or stop. In order to succeed, it must navigate to the proximity of the target, look at it, and issue the stop action. Note that multiple stops are allowed in our setup to encourage the exploration. The learning process can be formulated using deep reinforcement learning. We take proximal policy optimization as our RL training algorithm. The agent receives a positive reward for success and a small negative reward as a time penalty at each time step. Besides, it also receives a collision penalty each time it collides with the objects and a penalty for wrong stops. This is the learning network architecture. A joint feature vector can be obtained by concatenating different encoded observations. The joint vector is passed to a memory unit to encode the history and the actor-critic model samples and action for the agent to take in the environment. The next section covers our experimental results. We use two metrics to evaluate the navigation performance. One is success rate, the other one is success rate weighted by path length. We use three methods for evaluation: baseline, referencing gesture, and intervention gesture. Those two charts show the navigation performance at the test sets for different methods measured at the first stop. As a comparison, we add the results from another work, a similar setting, but uses additional scene prior knowledge. We can see that referencing and intervention gestures perform much better than the baseline method, of which the intervention gesture is a more effective kind of gesture to communicate with the agent. This table summarizes the performance of the agent with different number of stops. We can see that our agent performs much better with higher number of allow stops, and the improvement of the metrics with gestures is more evident in a lower number of allow stops. To visualize the effectiveness of our method, we show some qualitative results here. Compared with the baseline method, where the agent often struggles to find the target, our referencing gesture model enables the agent to navigate to the target more intelligently. As to the intervention gesture model, our agent is able to understand the gesture and reacts to it by rotating until it faces the target object before moving forward. This example illustrates the overview of our method for inference with human in the scene. The human user is situated in the virtual environment and gives the agent a direction to the target object in the room using gestures. Body and hand key points are detected by connect and lip motion, then passed to the agent. The agent sees the gesture and starts navigating the room until it reaches the target destination. This is another example with intervention gestures. The agent starts navigating the environment, and the human user instructs the agent in a rejective manner when it intends to move in the wrong direction. The agent understands this gesture and turns in the correct direction until it finds the target. To summarize, our work is the first incorporating human gestures for embodied agent learning and showing the agent can learn the semantics of gestures without supervision. There are future works, including adding more objects and targets, defining more complex tasks, and allowing multiple agents in the scene. We could also allow agents to show gestures in response to human players. Thank you.